Hello and welcome to another episode of Chemistry with Harvey. Today we're talking about catalysis. Catalysis is a property of transition metals that occur because of their ability to lose and gain electrons, or their variable oxidation states. It's quite a useful property as it allows us to use them to speed up several different kinds of reactions, which we're going to learn about today. So the first thing we need to know is how they work as catalysts. Basically, the reactant or the reagents adsorb, that's with a D, to the surface of the transition metal. This is very different from absorbing. Absorbing is when they chemically bond. Adsorbing is when they just stick to the surface. Then the reactions take place, and then the reagents deadsorb again and fall back off the surface of the metal. It's very important that you understand the difference between absorb and adsorb. It's quite similar spelling and pronunciation, so it can be a bit confusing. The effectiveness of a catalysis is dependent on how strong the bonds are between the catalyst and the reagents and the products, because if the bonds aren't strong enough, then the reagents won't adsorb to the surface of the catalyst, and if they're too strong, then they stay there, and this causes catalytic poisoning, where the reagents never fall off. The products never deabsorb from the catalyst. So there are two types of catalysts that we need to know about, heterogeneous and homogeneous. And as you can probably tell from the roots of their names, hetero means different or opposite, and homo means the same. And when they refer to difference or opposites, they are talking about phases. Phase is a new word that we've just come across. It means that there's no barrier between the catalyst and the reactants. For example, if you have a solution, the solvent and the solute are in the same phase, although they are in different states. This is because the solvent and the solute are mixed together and they can interact with each other. On the other hand, if you have a gas and a chunk of transition metal, they are going to be in different phases because the gas and the solid can't mix together. We're now going to take a look at some catalytic reactions that we need to know for the syllabus. We're going to start off with the heterogeneous reactions that we need to know, and the main one is the contact process. It's also worth knowing the Haber cycle, but that's going to come up less, so we're going to look at the contact process in more detail here. This is the production of sulfuric acid from sulfur and oxygen, and this middle phase, phase 2 here, is where we use a catalyst, and we use a vanadium catalyst of V2O4 or V2O5 to speed up the process. So we can have a look at that reaction now. The sulfur dioxide and the V2O5 form sulfur trioxide and V2O4 as the first reaction, and then the V2O4 reacts with oxygen again to form V2O5, and that process there is 2 steps and has a far lower activation energy than the SO2 reacting directly with oxygen. So the catalysis works, and if you remember from GCSE, we can look at a catalysis graph to show the difference in activation energy when using a catalyst versus the original reaction. Now we can just quickly look at what makes this a heterogeneous reaction. So if we look at the catalysis reaction, you can see that all of the reagents and products are gases except for the ones including vanadium, which are your catalysts. So the gas and the solid are in different states and different phases, so it's a heterogeneous reaction. Next, we're going to look at the homogeneous reactions that we need to know for the syllabus, and there's 2 of these. The first is peroxodisulfate ions reacting with iodide ions, and this is a very slow reaction on its own because they are both negative ions, so the electrostatic forces are going to repel them away from each other, making interactions far less likely than with normal molecules. This reaction uses an Fe2+ or Fe3+ catalyst, which speeds up the reaction dramatically as it is now negative ions reacting with positive ions. So this is a different type of catalysis to the original one. The original one with a difference in activation energy, and this one is an increase in collision frequency. You may have noticed in the first reaction as well that in all catalyst reactions there are 2 steps. This is because catalysts have to be reusable. In one step, the catalyst is oxidized, and in the other, it's reduced. So it's a cycle of just constantly reducing and oxidizing the catalyst. The final example we're going to look at is an example of autocatalysis. This is the case of the oxidation of ethanoic acid by manganate 7 ions. The catalyst for this reaction is actually a product of this reaction. So we call this an autocatalysis reaction, as the product is produced during the reaction. This gives the reaction a very strange concentration time graph, as the reaction starts off slow but then builds up pace as more of the catalyst is produced, and then it begins to slow down again as the reactants start to diminish. Thank you for watching this episode of Chemistry with Harvey. If you have any questions, do please comment below, and I will see you soon for our next lesson.